Welcome back, students. Now in the previous section we saw how liver utilizes carbohydrate during fasting. So now let us look at what are the changes that are happening in the liver as far as lipid metabolism is concerned. Now what do you think are happening during lipid metabolism? Now basically during fasting we need to adipocytes are going to release more and more fatty acids. When adipocytes are releasing more and more fatty acid, they all reach the liver. So fatty acids reach the liver, and this fatty acids, what do they form? They form acetyl-CoA, which enter into the TCA cycle. So acetyl-CoA is the source, increased fatty acid oxidation is the source for energy to the liver cells. What else is happening? Now liver is a site where, as far as lipid metabolism is concerned, is a site for transport of endogenous TAG. So is lipogenesis taking place? No, lipogenesis does not take place in the liver during the fasting. So the amount of VLDL that is going to travel from the liver to other tissues is going to decrease. So VLDL formation decreases. So let us look at what is happening in the liver. Beta oxidation of fatty acid is the major source of energy to hepatocytes. Now in this, beta acetyl-CoA carboxylase, which is the regulatory enzyme of de novo synthesis, is phosphorylated and inactive. So what does it mean? De novo synthesis of fatty acids is not going to take place, nor is VLDL formation. So when acetyl-CoA carboxylase is inactive, it removes the inhibition on carnitine palmitoyl transferase 1. It will see that more and more fatty acids are going to enter into the mitochondria and undergo beta oxidation. And this provides the NADH and ATP that is required for this gluconeogenesis. For gluconeogenesis we need energy. So from where does this energy come? It comes from fatty acid oxidation. This will give the energy that is required to convert glucose 6-phosphate to glucose. Remember, it has come from either the amino acids have come, everything has come, but if the liver itself is not having energy, how can it produce glucose? So all this energy for this comes from beta oxidation. So let us look at further what happens. Now as I said, acetyl-CoA can enter into the TCA cycle to give energy. Does it really happen? What is happening? For acetyl-CoA to enter into the TCA cycle, what is required? We require oxaloacetate. And where has oxaloacetate gone? Oxaloacetate has gone for gluconeogenesis. So when oxaloacetate is diverted for gluconeogenesis, what will happen to acetyl-CoA? It will have an alternative fate, and we call this as ketone body formation. So acetyl-CoA will not enter the TCA cycle. Most of it will undergo beta oxidation, gives it the energy that is required. And this acetyl-CoA goes into ketone body formation. What will it do with these ketone bodies? What will happen? Can the liver use these ketone bodies? No, it is lacking in the enzyme thiophorase. So the liver cannot use these ketone bodies. It will water soluble ketone bodies, so it will diffuse out of the liver into the circulation. From there, where does it go? These ketone bodies will travel and they can provide energy to the brain or to the skeletal muscle. So ketone bodies form an alternative fuel even for the adipose tissue, for the brain and for the skeletal muscle. So the ketone bodies have formed and ketone bodies have been released to the extrahepatic tissues. So the liver synthesizes and releases ketone bodies. Now which is the main ketone body? 3-hydroxybutyrate. Acetyl-CoA increased because of beta oxidation cannot enter, and it enters into ketone body formation. And these are used by extrahepatic tissues including the brain. I'll talk to you. Till now I was talking glycogen, which has provided glucose, gave energy to the brain. You had gluconeogenesis, which formed glucose, which is giving energy to the brain. But now the brain has switched over. The brain has changed. It has changed its preferential fuel from glucose to ketone bodies. Minute it sees ketone bodies, okay, fine, I have to use ketone bodies, the brain realizes, and the brain cells start using ketone bodies as a source of energy. Why does the brain switch over? That is mainly to spare glucose for tissues which cannot have any other source, like the RBC, cornea, or the lens. So, including the brain can use ketone bodies. So, at the same time, what else it is doing when it is switched over to the use of ketone bodies? What else happened? Remember, from where did this glucose come? It came from muscle protein breakdown. So, only when the muscle proteins were broken down, they could give the gluconeogenic precursors, and the liver was able to synthesize glucose. If the amount of glucose it was required is minimal, and the brain switches over to ketone body, this whatever little glucose is enough for the different glucose tissues which are dependent entirely on glucose. So what it has effectively done, minute it has shifted over to ketone body metabolism, it has spared the muscle proteins. So because it has shifted over to ketone bodies, the muscle proteins are spared. So and plus once the muscle proteins are spared, the essential proteins, wherever these amino acids are required, for example, liver is to synthesize an essential protein, maybe a clotting factor, maybe albumin, maybe immunoglobulins. For all these amino acids, let them be used for all those things rather than for glucose. So the brain is going to switch over to ketone body formation. Remember, they are fasting, their chances of infection are more, the body will be more stressed out. So the body doesn't want to do all that. So what it says, okay, amino acids, you go for synthesis of essential proteins. I'll use some other mechanism to sustain myself, and that comes from ketone bodies. And where have the ketone bodies come? They have come from the adipose tissue. So let us decrease the adipose tissue content within the body and see to that I also survive, you also survive. So these organs talk between themselves. The inter-organ relationship is happening. So they spare the proteins that are essential proteins are not degraded for the sake of gluconeogenesis. And ketone body concentration increases in the blood as the fasting progresses. Now what is happening? As I said, in the liver it is happening. All this carbohydrate, protein and lipid metabolism. We saw how it is happening in the liver. Now let us look at the adipose tissue. What is happening in the adipose tissue? Adipose tissue has to release, as I said, fatty acids. So from how did it release? Again, glucagon. What does glucagon do? It phosphorylates. What does it phosphorylate? Hormone sensitive lipase. What is hormone sensitive lipase? It is something which is going to break down the TAG that is present. So what it does, all the triacylglycerol in the adipose tissue is going to be broken down into glycerol or fatty acid. Both of them go to the liver, fatty acids form ketone bodies, glycerol go for gluconeogenesis. So, what about carbohydrate metabolism in adipose tissue itself? Is lipogenesis taking place? Are there chylomicrons which are giving it TAG? Is there any VLDL which is giving it its endogenous fatty acids or triacylglycerol? None of these are there. Chylomicrons have to come from intestine, and intestine, no food intake. So no TAG is going, no lipid is reaching the adipose tissue. So no lipid is reaching the adipose tissue. What about glucose? For glucose to enter, for its own metabolism, for glucose to enter into the adipose tissue, we need glucose transporter 4. And what is this glucose transporter 4? It is insulin dependent. No insulin, these glucose transporters are not going to the membrane, and glucose will not enter into the adipose tissue. So effectively, adipose tissue has decreased its use of glucose. Why? Spare the glucose for tissues which need it. So the adipose tissue also switches over. Maybe it will go in for beta oxidation for its own cell requirement. At the same time, it undergoes lipolysis. Remember, lipolysis does not require any energy. It has to just keep on breaking down. So if you look at adipose tissue, no insulin, so glucose entry is decreased TAG synthesis, lipogenesis will not take place. If you look at fat metabolism, there is stimulation of the hormone sensitive lipase by glucagon, epinephrine and norepinephrine, which is released from the sympathetic nerve endings. Remember, all these hormones were released from epinephrine and norepinephrine. All these hormonal changes I've told you which are happening, they all stimulate hormone sensitive lipase. So this releases fatty acid which are used by the adipose tissue for its own needs, that is beta oxidation, or it is transported to other tissues. Now the glycerol that is released will go for liver for gluconeogenesis. As I said, there are no chylomicrons, no VLDL, so lipoprotein lipase activity is low. So there is no hydrolysis of the circulating THE of lipoproteins. In case if they are there also, it is going to decrease. Now let us look at the skeletal muscle. Fasting, resting skeletal muscle. We are not talking of a person who is fasting at the same time exercising. Let us look at only the fasting, resting skeletal muscle. So what happens to carbohydrate metabolism? Again, remember, it is the adipose tissue and skeletal muscle which are dependent on insulin for glucose transporter 4. Remember, the glucose transporter 4 is insulin dependent, and this has to be translocated from the cytoplasm to the cell membrane, and then glucose will enter the cell. Again, no insulin, no glucose transporter 4, and the glucose cannot enter into the skeletal muscle. Glycolysis is decreased. So what is happening within the cell? What gives the skeletal muscle the energy it requires? It cannot get it from glucose. It can get it from ketone bodies and also from fatty acid. One is ketone bodies and the other is fatty acid. So this fatty acid from DHA hydrolysis also gives it energy. Adipose tissue fatty acids can undergo beta oxidation, and acetyl-CoA is formed which can enter the TCA cycle, give it energy. Ketone bodies also can give it energy. At the same time, in the muscle protein is undergoing breakdown. Glucose alanine cycle is taking place. All the amino groups of the proteins are transferred to alanine, and alanine is going to the liver, and there it is going to go provide substrate for gluconeogenesis. So let us look at it. Carbohydrate metabolism, no insulin. Lipid metabolism, first 2 weeks they use fatty acids and ketone bodies as fuel. After about 3 weeks, it starts using fatty acids exclusively. So after about 3 weeks of fasting, 3 weeks of starvation, it says, I don't want ketone bodies. Let the brain use the ketone bodies. I will start using only fatty acids. So it switches over. And there by that time the brain has switched over from glucose to ketone bodies. So all the tissues are happy. And the liver is synthesizing more and more ketone bodies. So it switches over to exclusively to fatty acids. And this increases the ketone body levels and helps the brain. Protein metabolism, remember, first few days rapid breakdown of muscle proteins to provide amino acids for gluconeogenesis. The most important are alanine and glutamine. Branch chain amino acids are also catabolized. But after a few days, once the brain starts utilizing ketone bodies, the muscle protein says enough. Let me not break down anymore, and the muscle protein lysis decreases. As the brain switches over to use ketone bodies, muscle protein breakdown slowly decreases. This is what happening in the resting skeletal muscle. We finished the adipose tissue, hormone sensitive lipase, we finished the liver, we finished the skeletal muscle. Now let us look at the brain. During the first days of fasting, brain continues to use glucose exclusively as a fluid, and this glucose comes from hepatic gluconeogenesis or glycogenolysis. But in prolonged fasting, as the plasma ketone bodies level increase, the brain starts using ketone bodies. So this is the summary of what is happening in different tissues during fasting. So the main priority is to maintain blood glucose levels for tissues which are dependent on glucose. Now the hormones involved are insulin is decreased, glucagon is increased, epinephrine is increased, cortisol is increased, norepinephrine is increased. There are certain enzymes activated and deactivated. Hormone sensitive lipase is activated. Glycolytic enzymes are deactivated because we want to switch over to the formation. Gluconeogenic enzymes are activated. First few hours, hepatic glycogenolysis, followed by hepatic gluconeogenesis. And the substrate for this gluconeogenesis comes from lactate, muscle protein breakdown, and from glycerol. Then further, THA breakdown in adipose tissue due to hormone-sensitive lipase. Fatty acid oxidation in most tissues, liver, muscle, etc. Then comes hepatic ketogenesis, ketolysis in extrahepatic tissues including brain, and finally spares the muscle proteins from further degradation. This is what is happening during fasting. This is a summary. Now I'll talk about one more important condition, that is stress. What are the hormonal and metabolic changes that are happening during stress? Now, conditions which lead to stress will stimulate the hypothalamus to release CRH, corticotropin releasing hormone. CRH will stimulate the pituitary glands to increase the secretion of ACTH. And ACTH will stimulate the adrenal glands to secrete cortisol, adrenaline, and the autonomic nervous system to secrete noradrenaline. Increased blood adrenaline levels will inhibit insulin secretion and stimulate glucagon secretion. So it is the adrenaline which is inhibiting the insulin secretion. So why am I talking about this? Suppose somebody is stressful and he is taking in food also at the same time. What will happen? The glucose should stimulate insulin secretion. But during stress, we don't want the insulin. Adrenaline is going to overcome the stimulation of glucose and inhibit insulin secretion, and see to that it is the glucagon which is going to increase during stressful conditions, so that the body is geared up for fight, flight or fear situation. So let us look at the schematic diagram. Stress, the pancreas, beta cells, alpha cells, we saw how decreased insulin, increased glucagon. Now if once epinephrine is there, it will override the inhibition or the stimulation of glucose by stimulation of beta cells by glucose to release insulin. It also stimulates the alpha cells to release glucagon, and thereby all the actions that we saw now, what were happening during starvation, the same thing can happen during stressful situation. And why this is happening? So that the brain can start utilizing more glucose. Okay, so increase in blood levels of glucagon and cortisol will stimulate glycogenolysis in muscle and liver, stimulate breakdown of protein in muscle, and stimulate lipolysis and mobilize fatty acid from adipose tissue for peripheral tissues use, and stimulate indirectly, it will stimulate ketogenesis as a result of the increased production of acetyl-CoA, where fatty acids are used as the main source of energy by peripheral tissues. And it also stimulates gluconeogenesis in liver and kidneys due to increased levels of blood amino acids as a result of protein breakdown in muscle. Now I'll just give you a brief summary of the different enzymes. We kept on talking of different allosteric modification by different enzymes. Now we'll just look at any of these pathways. They are controlled because of 4 factors. One is substrate availability. If substrate availability is not there, the enzyme cannot act naturally. There is no substrate, so it cannot act. Secondly, it may be because of all these enzymes in different pathways can be regulated allosterically. Now, in allosteric regulation, please know that allosteric regulation is occurring within few minutes to minutes it is happening. Minutes to hours allosteric regulation is happening. Then the third level of regulation comes at the level of covalent modification, and this is taken place by phosphorylation, dephosphorylation, again by hormonal action. So you have substrate availability, allosteric which is happening within minutes to hours, covalent modification between hours to days, but more than that, more regulation is done by induction and repression, again by hormones, but this will take certain days to take effect. That is how all these pathways are going to be regulated within the body. Some pathways are going to be switched on, some pathways are going to be switched off by these 4 mechanisms only. Now let us look at a brief summary of all the allosteric regulators of the different pathways. This is again an MCQ point of view, that is why I am talking. Now remember, any catabolic pathway is all dependent upon the energy status within the cell. And which are the energy status indicators? ATP, ADP, NADH, NAD+. ATP is more, energy is good, catabolism need not take place. NADH is more, energy is good, catabolism need not take place, whereas the anabolic pathway should take place. So these regulators, different regulators, allosteric regulators, I have listed it out here from the sake of MCQ point of view. Now let us look at glycogen degradation. The regulatory enzyme is glycogen phosphorylase. Its activator is AMP and its inhibitor is ATP. Why? Energy status. High ATP, you don't want glycogen degradation to take place. Energy is good, I don't want glycogen to be degraded. What about glucose oxidation? Phosphofructose kinase 1, pyruvate kinase, pyruvate dehydrogenase is activated by AMP. Why? Energy status is low. Let glycolysis take place and form ATP. Once ATP is formed, ATP is going to act as an inhibitor. ATP is going to act as an inhibitor. Citrate is also another energy indicator. So citrate will also inhibit ATP. All these are the different enzymes and their activators and inhibitors. You can pause the slide at now and look at the different activators and inhibitors of the TCA cycle, of gluconeogenesis, of fatty acid synthesis. So you look at the different activators and inhibitors. All these are allosteric regulation. Now we kept on talking of covalent modification. Now out of covalent modification, again I have given out the list out here, different enzyme and whether they are all phosphorylated, in the phosphorylated state whether they are active or inactive. In this you can see glycogen phosphorylase, phosphorylase B kinase and triacylglycerol lipase or hormone sensitive lipase are the three enzymes which are active in their phosphorylated state. This is the take-home message as far as integration of different metabolic pathways are concerned. And this is how by phosphorylation, dephosphorylation, allosteric modification, all this integration is taking place at the cellular level and at the interorgan level. So with this we come to the end of integration of metabolism. Thank you.